Time for more questions and answers. This is for the second week. These are questions for my small group in 101, but I know everybody always has the same questions, so let's just answer them publicly. Let's see, since we disregard a lot right now, like friction and air resistance, how accurate can we be right now in terms of real situations? The answer is not too accurate. So wind resistance or air resistance is pretty strong. If you're dealing with heavy objects dropping, then it's pretty accurate that resistive air drag is not very large. Like when I dropped the steel and aluminum balls, they fell exactly together. But if you're talking about dropping something lighter, like this question, then air resistance is huge. But we'll be getting a little more realistic as time goes on. Will we do a lot of questions with non-constant acceleration? Not a lot of questions. We'll do a lot with constant acceleration. We'll do a lot with constant acceleration that changes in time. Right, so it's constant for a while, then it comes here, it's constant, and then it goes negative, kind of like in the Super Karate Monkey Death Car problem. But ones where it really changes and you have to use an integral, we'll have some of those to make sure you really are tested on everything, since it is calculus-based physics, but the majority will be regions of constant acceleration. I'd like to go over the integrals of velocity and acceleration again more conceptually. So I'd recommend the videos, the calculus of velocity and the calculus of acceleration. Have a look at those here on the YouTube channel. Which formulas do we need to know for this class? All of them. Is downward acceleration the same when objects are ascending, or does the upward momentum make a difference? Excellent conceptual question. So the answer is yes, it is the same. So, and no, the momentum does not affect the acceleration. So if it's talking about just the acceleration due to gravity, it's always straight down. Whether the thing is moving up or moving down, it's always accelerating down. Like if you imagine I throw this chalk, it was always decelerating. It was always decreasing its upward velocity and increasing its downward velocity. Its actual state of motion doesn't make a difference for gravity. Now you could have other physical systems where the acceleration does depend on something. But if you're just talking about gravity and trajectories, it's always down. Doesn't matter how the object is moving. Do we need to memorize the kinematics equations? Yes. My high school physics teacher recommended that I solve questions using conserved values instead of kinematics equations. Why is that better? So I would say it is not better. It is just two ways of doing it. What you really need to learn is, once you've seen everything, is figure out these kinds of problems are better with conserved energy and momentum, and these problems are better with kinematics. And you got to figure it out kind of case by case. One is not really inherently better than the other. And since we haven't even done the conservation yet, do everything with kinematics. What will we need to do with multivariable calculus you showed us yesterday? Yes, so I went off and talked all the way through multi in class. That was just for enrichment. So don't worry about it. That was just if you're in multi now. I thought that might have been interesting to you. Are integrals and derivatives opposites of each other? In a sense, yes, they are. Will we be given any formulas for the exam? No. When does T naught not equal 0? So I've said a lot about, oh, you should always make T naught 0. I mean, why wouldn't you? What I really meant was you should always make T naught the beginning of the region you're thinking about. If you were doing this problem, you'd calculate this part where you'd have T naught there. Then you'd calculate this part and put T naught there, or Ti initial. You calculate this part, you'd put it there. You move it to be wherever you want. And it might not be the absolute 0 on the origin. But you move it around so that you can solve the problem. But you got to keep up with where you had it each time. This created some confusion on one of the pledge problem questions where it wasn't clear exactly what was being asked, and we fixed that. But in general, no, T naught doesn't have to be 0. You can make T naught anything you want T naught to be. How well will we be needing to know how to do dimensional analysis? So, not really. Again, that was more for enrichment, although there was homework about it, but you'll notice there was no pledge problem question about it. So usually what we put on the pledge problem is a pretty good hint of what's going to be on the exam. So you're probably done with dimensional analysis, although you may use it to help you solve problems.